LeChat's principle. That is another topic of equilibrium that we're going to be discussing. You actually already watched a video on this, as I already mentioned. The whole idea is when you have a system that's at equilibrium and you cause a stress to that system, and there's several different ways to cause stress to a reaction, the reaction will have to go back to equilibrium. Like, it will eventually get back to equilibrium. And so we're going to be looking at, if we have a system at equilibrium, we cause a stress to change that equilibrium position, how does it get back to equilibrium? Okay? So how does the reaction respond to each type of stress? Okay. So we have this reaction. It didn't say this because for some reason there's a typo, but what state of matter does that O2 have? Gas. Oxygen is pretty much always going to be a gas. All right. So if we were to increase the amount of H2O, how would that affect the equilibrium? I want to get the wrong answer first. You can give me the wrong answer? Okay, what's the wrong answer?
It would shift to the left.
The wrong answer is that it would shift to the left. So you might think, oh yeah, it's going to shift to the left because H2O is a product, and we're going to shift away from additions, right? But why is that the wrong answer? Because it's a liquid. And remember, solids and liquids don't affect equilibrium. So it doesn't matter if you change the amount of a solid or a liquid substance because it doesn't go in the equilibrium expression. So what is the real answer for this problem? No shift. Because H2O is a liquid. All right? What would happen if the temperature of this reaction were increased? What do we look at first? We look at the enthalpy change that's given at the beginning of the problem. Okay? The delta H is negative 1,036 kilojoules. What does that mean? Good, it's exothermic. See how everything kind of interrelates with everything we've been learning? It's not, distinct units. It's all together. So this is an exothermic reaction because it's negative. In exothermic reactions, what is happening with heat? Is it being absorbed or released? It's being released. Good. In exothermic reactions, the reactants produce energy in the form of heat as they form the product. So heat is also a product for exothermic reactions. So we can write plus heat on the product side. If this were endothermic, heat would be a reactant, and we could add plus heat to the reactant side. So now we're treating this like a product. If we increase the amount of that product, which way is it going to shift? Left. And what else changes as a result of this temperature increase? What is dependent on temperature? I mean, the things you're saying aren't wrong, but what is the title of this unit? Equilibrium. So what about the equilibrium is also temperature dependent? Kc, the equilibrium constant. That's where I was going with that. Okay? So Kc, the equilibrium constant, is also going to change. Temperature changes are the only thing that also affect the equilibrium constant. All right? So since this temperature change is causing a shift to the left, our Kc value is going to decrease. And the reason why is because, remember, Kc is products over reactants. If our shift to the left, if our temperature change causes a shift to the left, that's increasing the amount of reactants. That's what the R stands for. That's increasing the amount of reactants or decreasing the amount of products. No matter which one you do, which one you're looking at, this whole value is going to decrease because that's how math works, right? If your temperature change causes a shift to the right, no matter if it's endo or exo, if your temperature change causes a shift to the right, Kc would increase. Okay? All right. What if we were to change the volume of the container? What substances do we care about when we're changing volume or pressure? Gases, because gases are influenced by volume and pressure changes. How does volume and pressure relate? More specifically, they're inversely related, right? Okay. Pressure and volume are inversely related. So, if we decrease the volume, you could also say that's increasing the pressure inside that container. I like to put it in terms of volume, though, because when you decrease the volume, the smaller volume, you go to the side with the smaller number of gas moles. You're going to shift to the side with the least number of gas moles. So let's look at our reaction. How many moles of gases do we have on the left? 5, because we have 2 and 3. And how many gas moles are on the right? 2, just the SO2. So which side has the least number of gas moles? The right. So this change would cause a shift to the right. Good. And how would that affect my Kc? We're shifting to the right, so Kc should increase, right? Kc doesn't change because the only thing that can affect equilibrium constant is a temperature change. And we didn't change temperature here, so Kc stays the same. So don't get tricked. Okay? All right, for the last one, the amount of H2S is decreased. Which way are we going to shift? To the left, because we're removing some of this reactant, and the reactant is gaseous, so it will affect the equilibrium position by changing the amount of it. So we're going to shift left. And what happens to Kc? Nothing, because it didn't change, because we did not change temperature. What questions can I answer for you about that? I mean, definitely great multiple choice questions because there's no math involved in it, but don't think that it won't be solely multiple choice. Okay. All right, I'm going to pause the video for a moment. All right. Last topic for this unit is how kinetics and equilibrium relate. All right. So back in unit 4, when we talked about mechanisms, we wrote rate laws based off of what? Which step? The slow step, because the slow step is also called what? The rate determining step. So in this reaction, or this mechanism, this second step is my rate determining step, right? Well, okay, let's just go ahead and, based off of this mechanism, based off of the stuff we learned last unit, take a moment to write that rate law. And what do you get as the rate law? You should get this, right? Rate equals K times the concentration of NOBr2 times the concentration of NO. Both of these are what order? First order, because they both have coefficients of 1 in the slow step. All right. So, what can be said about NOBr2? What type of substance is this? Yes, it's an intermediate. Yes. It is an intermediate. Okay. because it is an intermediate, we cannot directly measure and monitor the amount of NOBR2 that we have in this rate law. We cannot directly measure it. We can indirectly measure it because we know that its amount is dependent on the amount of NO and BR2 that are reacting in the first step. But because we cannot directly measure it, it technically cannot go in the rate law. So, I lied to you last unit. Last unit, I was like, yep, this is the rate law. Well, that's not 100% correct because technically, like I said, we can't have this NOBR2 in the rate law because it is an intermediate. It is not an actual reactant. Okay? So, we are going to have to do a substitution. What can be said about our first step that's related to stuff we're learning this unit? It's at equilibrium. See how it has that double arrow right here, and it also tells you it's in equilibrium? So what expression can we write about the first step? The Kc expression, the equilibrium expression. And what will that look like? And I meant to say this, but we're going to assume that all of these substances are gases or aqueous. Okay? All right. So now we know that that is the equilibrium expression. Let's go ahead and rearrange that to solve for NOBR2. Hold on. I want to move that down. I want to write that below. If I rearrange this to solve for NOBR2, what do I get? I get this, right? And now I can take this whole thing and substitute it in for this, right? So I get rate equals rate constant times Kc times concentration of NO, because right here, but wait, we already had an NO in the rate constant, or sorry, the rate law, so it's going to be concentration of NO squared times the concentration of Br2. We're not done. What does little k mean? What does that stand for? Rate what? The rate what? The rate constant, yeah. What is Kc? The equilibrium what? Constant. So we have a rate constant times an equilibrium constant. What is a constant times a constant? Still a constant, right? It doesn't cancel out. It's still a constant. Its value is different from either of the constants that we had, but it's still a constant, right? So we can call it, like K prime, not a derivative. It's just a representation that its value is different from the original rate constant and Kc. Every time we've been doing this, K prime is just a representation that it's different from the actual rate constant. Okay? So that's our true rate law right there. Because NO is a reactant that we can affect and we can influence and directly measure its concentration. Br2 is also a reactant that we can directly measure and affect its concentration. Okay? Yes, sir.
Do you have to show all the steps every time you do this at the
No.
I did.
Okay. All right. Why don't you guys try the next one? Does everyone have their packets with them today?
I do that.
You do? Okay, so I want you guys to be doing this one. Okay? I'm going to pause it while you do this. So those of you watching at home, why don't you go ahead and pause it and attempt this video, or attempt this problem. All right, so now that you've had a moment to do this problem, what's my original rate law? And both of those are to the first power. Okay, which of these substances are we going to have to substitute? The Br, because the Br is is the intermediate. So we got to get rid of Br. So we're going to write the equilibrium expression for the step before it because that's in equilibrium. And what does our equilibrium expression for the first step look like? Looks like that, right? And then we need to solve for Br in that equation. Okay? Do you want me to go through step by step? Okay. Okay. So when you solve this for Br, what do you get?
KC times BR2 raised to 1 half. KC is a constant, so you don't have to prove it.
Well, but if you're square rooting Kc, is it a different value? Yes, so you have to say that it's Kc to the 1 half. You can't just leave it as Kc because its value is different. It's whatever the original Kc was raised to the 1 half power.
Could you also just square the initial rate law?
But then that would be saying everything's to second order, and it's not. And then Br2 to the 1 half. It's possible to have 1 half order? Yeah. We saw a problem like that before. If you're the person asking questions about this, you shouldn't be talking while I'm going over it. All right, so now we're going to substitute in all of this for my Br. So I'm going to get rate equals K times Kc to the 1 half times Br2 to the 1 half times H2, technically to the first, right? And then all of this becomes what? K prime. Because they're all still constants. Oh, so close to being muted during that. And there is my rate law. Okay? No. So now we're going to go back and do some of the rice table problems that we did not get to previously. So go ahead and turn back to number 12. All right, like I said, we didn't quite get to these last few problems. We're going to do the last 3 problems from your in-class problems, and then we're going to go look at one from your guided notes, one that I want to touch on. I meant to put one in the in-class problems, and I forgot to. All right, so let's review this. We're going to set up a rice table. So those of you who were not here on Monday, this is really beneficial. Yeah, Okay, so what's my reaction? 2NO2 goes to N2O4. All right. What are my initial amounts of both of these things? We've got 0.015 for the NO2 and 0.025 for the N2O4. Okay. Before we move on, let's go ahead and write the equilibrium expression for this reaction. What does that look like? N2O4 over NO2 squared. And both of those are concentration. Alrighty. I am starting with some of both of my substances. I have a little bit of everything, right? So how do I know which way the reaction will proceed? We gotta calculate Q. Remember, the only way to know for sure which way it will, let me rephrase that. You can get away without calculating Q if you have 0 of something initially, but we have something of everything, okay? So we're going to have to calculate Q. And remember, Q is the equilibrium expression, or the equilibrium constant, but using initial values instead of equilibrium values. Okay? So my Q is going to be 0.025 over 0.015 squared. So go ahead and calculate Q. What'd you get? Like 111.11111111111 and so on and so forth. Yeah, so 111, right? How does that compare to K? Is that bigger than or smaller, greater than or less than? There we go. Words. That is smaller than or less than K. See, Kc is 170. So remember, when Q is less than K, we're going to go this way. Right? We're going to proceed towards the products in order to reach equilibrium. So my changes, my N2O4 is going to have to increase by some value. And therefore NO2 is going to have to decrease by what? 2x, because we maintain stoichiometry. So for equilibrium, I'm going to have 0.015 minus 2x for NO2 and 0.025 plus x for N2O4. Okay. And then I'm going to plug that all into my equilibrium expression. So 170 equals 0.025 plus x over 0.015 minus 2x, and all of that is squared. Okay? Remember doing this 2 classes ago? All right, and so just to solve it a little bit easier, I'm going to rearrange. Let me back up. Hold on, I'm getting ahead of myself. We eventually need to find x, but we have a quadratic here. I said this before, I don't care how you find x. As long as you find x correctly and you're the one doing it, right? Looking off of your neighbor is not appropriate. There are many different ways to find x. Some of you might have that program in your calculator where you can just solve the quadratic, you plug everything in, and it's like, here are your 2 x values. Remember to pull the positive one. Some of you might be able to just calculate it by hand. Like, again, I really don't care. I find the easiest and quickest way, because remember, time is a factor here. We want to find ways that decrease our workload and decrease the amount of time we are spending. Let's pull the denominator over. So we get 170 times 0.015 minus 2x, and that's all squared, equals 0.025 plus x. And now I'm going to graph that. Clear out those equations. So now I'm going to graph both sides and find where the 2 lines intersect. Okay? So I'm going to get 170 times 0.015 minus 2x quantity squared. And I'm not going to FOIL that. I'm not going to, multiply that out. Might as well leave it, right? Don't waste time if, you can help it. And the other side is 0.025 plus x. I typed everything in correctly. Now I'm going to press graph. You can't, as I'm knocking things over, you cannot actually see the other equation or the other line right now, it's too zoomed in. It's like a giant parabola. Okay, so if we wanted to see that, we could do zoom and then, what is it? Zoom fit, which is number 0. We could do that, and it'll like zoom out really, really, really far. And now you can't even really see the other one because it's so short. So we were, I think what we did, no, window, that's what it is. I'm going to make this really zoomed in. I'm going to make everything ones. I think that's how we did eventually see it. Oh, that's right. No, it's not a really big parabola. It's really close to the y-axis. All right, so anyway, so now we can kind of see both of them. Let me zoom in just a little bit more. There's actually two positive x values. Oh my gosh, I don't even know how I did that. Okay, let me zoom in. Zoom in. I don't know if I'm doing anything. Window. I'm going to make that 0.5. I'm going to make this really zoomed in. I'll eventually get there. I don't care about the y-min or the x-min. So I'm going to get rid of those. So 0.05. I think this is what the kid said last class, that works. Yeah, there we go. Okay, so there we go. That's why I wanted to zoom on. So we actually have two positive x values. I wanted to show you this, okay? So now if I go second calc, that trace button, and I go down to 5, it's going to ask me my first curve, my second curve, and then take a guess. It's going to right now find this x. That x is wrong. You should always be asking yourself, when doing these problems, does my answer make sense? If your x is negative, you have the wrong x. You need to go to the other x value. In this particular problem, we have two positive x answers that mathematically work out for this equation, but only one of them makes logical sense for chemistry. The x that we found right now, the 0.015, doesn't make logical sense for chemistry. Because if you plug that in, finding your concentrations, you're going to end up with a negative concentration for your NO2, which doesn't work. That doesn't make sense. Because if you plug in 0.015 right here, 2 times 0.015 is 0.03, and then 0.015 minus 0.03 is negative 0.015 molar, which can't happen. Okay, so you need to use the other x. So go back to the standard. I think that's, zoom standard. Go back to the standard. Give it a moment. Did I break it? Man, it is thinking for a really long time. Think I broke it. Second off? Okay. Everything's still good there. Windows back to normal. Okay, graph. Okay, there we go. Now we're back to normal. If you're back at the standard window and you go through the second calc or second trace down to 5, enter. Don't even try moving the cursor for guess, because it's gonna automatically go to the x that's closer to where the cursor is to begin with, and you should get that x value. So you want the one that's the other one, okay? This one makes sense. So 0.0013. Because it's small enough that it's not going to make either of, well, it won't make this negative because we're adding to it. It won't make this negative, okay? Because you cannot have a negative concentration. So again, don't just look at the number and be like, yep, I did the math right. Yeah, you did the math right. If you got 0.015 as your x, you did the math right. It just doesn't make sense for chemistry. Okay? So your N2O4 equilibrium concentration is what? 0.0263. Missing something. Molar, yep, because we have units on concentration. And NO2 equilibrium is what? 0.0124 molar. Good. And those numbers make sense because neither of them are negative. Okay? Let's do a couple others. Are we good? All right. So this one. Let's write out the reaction. Or let me write out the rice table. My reaction is NH4HS. That is a solid. Goes to NH3 plus H2S. All right, so in this reaction, we have a solid substance that's decomposing to two gases in a flask. Okay. What are my initial amounts of my two products? 0. I have none of them to begin with because all that's in the reaction container is the ammonium hydrogen sulfate. Sorry, hydrogen sulfide, the NH4HS. But that's a solid. So how much of this do we have? Does it say? No, it doesn't matter. Why doesn't it matter? Because it's a solid, so we can actually just cross that out. It's still in the reaction because without it, the reaction wouldn't occur because we'd have nothing to decompose, but the amount of it doesn't matter. All that matters is the equilibrium constant. Okay, but let's go ahead and write out that equilibrium reaction, or equilibrium expression. Kc equals, what's my equilibrium expression? And what goes on the bottom? Like 0 goes on the bottom? Technically 1 goes on the bottom, or we can just leave it blank, like I wrote here. Okay, but we don't put the NH4HS on the bottom because it's a solid. Okay. So since I have none of my products initially, which way will this reaction proceed to reach equilibrium? To the right. So both of these are going to be my plus x. And this is going to be x, and this is going to be x. It just goes towards the right. So now I can plug everything in. 1.8 times 10 to the negative 4 is my Kc, and what does that equal? X squared. Because that's all we have. Pretty easy, right? This problem's great. Nice and easy. So in order to find x, you just square root both sides. And what do you get as your x? 0.013? And then we can use that x to find my NH3 and H2S concentrations at equilibrium. They're going to be the exact same. Okay. Let's look at 13b. 13b, what do you notice about this problem? It's the exact same reaction as 13a. So we can write out my rice table. It's occurring at the same temperature because my rate constant is the same. This reactant is still a solid, so we can cross it out. But what's different? There's some NH3 already in the flask. We have some 0.02 molar NH3 initially. How much how much H2S do we have initially? 0. We still have none of it. So my changes, we're still going to proceed towards the right because we still need to make more H2S, or we still need to make some of it. Okay, so this is still going to be plus x plus x. But my change, how far it needs to progress towards the right, that it will change. So x is going to be a different value than it was in 13a. Because we don't have to go as far to the right to reach equilibrium because there's already some NH3 there. But unfortunately, we now have another quadratic. So we're going to have to go back to our calculator, go back to our equations, graph both sides, find where they intersect. Second trace, 5, enter, 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 there we go. And you should get 0.0067 as your x. Not as large as x was in the previous problem. Right? And your final concentrations for your equilibrium concentrations for your substances are different since NH3 started with some. So H2S is going to be 0.0067 molar. What's going to be NH3? Technically just 0.027 because of sig figs. But you see how sometimes the problems change that x just a little bit. One last problem I want to do, it's not in your in-class problems, this last one is in your guided notes. So please go ahead and get out your guided notes, turning to, I think it's page 10. We're looking at interactive example 13.10. You need them every class because you're supposed to bring them in your AP chemistry binder every class. All right, we don't need the calculator anymore. I wanted that to go away. I'm trying to make that calculator thing go away now. All right. So I understand that you already have this problem done because that was the expectation for this course, that you do your guided notes prior to learning the stuff in class. So I understand that you already have this problem finished in your guided notes, but I want to highlight a few things and go over it, okay? So you can follow along with your work that you already have written down on your paper. So let's write out the reaction. What are my reactants for this problem? This should be real easy because you already have it written out. And how do I write carbon monoxide? CO plus H2O. And what is that form? Plus H2. Good. What states of matter do all of these substances have? Gases. This is a rare case where we actually have water in the gas state, so its amount will affect the equilibrium expression, and it will go, or equilibrium constant, and it will go in our equilibrium expression. So let's go ahead and write out the equilibrium expression for this reaction. Yes, which you've already done. So what goes on the top? CO2 times H2 all over CO times H2O. Yay. All right, what are my initial amounts of all of these substances? 1 molar. They are all starting off with 1 mole in that 1 liter flask. So every single substance has a 1 molar to begin with. So in order to figure out which way this reaction will proceed to reach equilibrium, what must we calculate? Q. Remember, Q is the equilibrium constant, but with initial amounts. So 1 times 1 over 1 times 1 is 1. So Q equals 1. How does that compare to K? It's less than K because K is 5.10. So which way will the reaction proceed to reach equilibrium? The right. So my reactants are going to decrease and my products are going to increase. So I'm going to have 1 minus x, 1 minus x, 1 plus x, 1 plus x. And I'm going to plug that into my equilibrium expression. What's going to be on the top? Yeah, it's 1 plus x squared. And on the bottom, we're going to have 1 minus x squared. Now, you could rearrange this, bring the denominator over, graph both sides, see where the reactions, or where the curves intersect. Or you could recognize that you have a squared over a squared. Or you could square root both sides and do the math that way, which is what the problem that you've already done showed you how to do. So when you square root both sides, what's the square root of 5.10? 2.26. So then you get 1 plus x over 1 minus x. And now you just have to do a little bit of algebra. Okay, I'll go through those steps for you guys. So when you bring this over, you're going to get 2.26 minus 2.26x equals 1 plus x. And now combine like terms, right? I'm aware. And x is what? Point what? 0.387, yes. One-third is not the right answer. No. On free responses, at no point should you be making an approximation. I'm making a point of that to mention that because the only time you're allowed to make approximations in math is for multiple choice. If it's a free response, you need to calculate the exact value. The only approximation you're doing is rounding for sig figs. Okay? So use the calculator on the free response. Okay? All right, so x is x is 0.387. So our CO2 and H2O equilibrium values are going to, CO2 and H2 equilibrium values are going to be the same, and it's going to be 1.387 molar. And our CO and H2O values are going to be the same at equilibrium, and it's going to be what? 0.613 molar. Okay. So the point of that was that when you have a perfect square on the product side, just take the square root of both sides. So 13.11, the next interactive problem, as you saw, because you all did the problems like you were supposed to, that walks you through a similar type of problem. And there's a homework problem in 5B. Hey guys, I shouldn't have to raise my voice because you're packing up while I'm still talking. Okay? In homework 5B, there was a problem very similar to this as well, which again, you should have already done because it was assigned on Monday.